Hello and welcome back to System Administration class. After we discussed the job of a system administrator in the last video, I wanted to introduce you to a few core principles that will important for us throughout the semester. More than just maintain computers and infrastructure components, system administrators control entire systems. With more experience and seniority, they are ultimately in charge of building these systems, of designing the infrastructure and its components so that the job title frequently morphs into that of a systems or network architect. So when everything is awesome, system administrators step into the role of planning, designing and overseeing the construction of a complete system suitable for the immediate requirements of today as well as anticipating the needs of the organization down the road. We become software builders. But in order to accomplish this, we need to build our infrastructure on two basic principles. First is you have the scalability and the security. Neither of these can be added to a system after it has been built. Trying to apply security after the system interfaces have been defined yield restrictions or limitations. Trying to make a system with inherent limitations perform under circumstances it was not designed for yields hacks and workarounds, and the end result frequently resembles a fragile house of cards more than a solid, reliable structure. But there is a third core principle that is necessary, and it is what actually enables these other two principles. Have simplicity. Simplicity is simultaneously obvious and counterintuitive. Simplicity underlies both scalability and security. Since reduced complexity implies better defined interfaces, minimize ambiguity in communications or data handling, and increase flexibility. As with the other two core aspects, simplicity cannot be added after the fact. It must be inherent in the architecture. Simplicity is the enabler of both scalability and security. Let us look more closely at each of these three core principles. Let's begin with scalability. Scalability is a buzzword often thrown around these days, asking, but that does it scale? Is an easy way to seem smart in meetings, but let's consider what scalability really means. Suppose you have a website and it becomes really popular. Say it was slash dotted. Oh, wait. You guys don't know what slash dot is. Let us say it was published on the Hacker News front page on a popular Reddit. The poor little web servers were not designed for the sudden increase of the traffic. In other words, you're getting a system overload. So now that whenever you have a resource issue like this, there's only so many options. On the one hand, you can have scale vertically. Scale, wi- scale vertically. That is, you get a better, beefier surfer to handle the increased load. Scaling vertically is great. It's usually quite easy to do as you don't have to change much. You buy the big ass horse here and off you go. So you're throwing money at the problem in the way, which is a great way of solving many issues if you have money. Also note, of course, that this only buys you time. At some point, you may have even too much of a load for even this monster to carry. So your other option is to scale horizontally. When you scale horizontally, you get more of the same and try to distribute the load. Scaling horizontally may seem a bit better here since it allows you to continue taking an additional load. You just need to keep on adding horses. I mean, servers. But scaling horizontally isn't quite as easy as scaling vertically. When you add more servers, you then need to distribute the load. So you add, say, a load balancer, which you now have to help check and maintain. That is your hiding complexity. But of course, you can also combine the two approaches. Get more beefier hardware and distribute across them. Oftentimes that's what people mean when they say scalability, but there's one aspect that is often overlooked. Once you've scaled up, either horizontally or vertically or both, you are now running with higher cost. That is, for true scalability, you also want to be able to scale down. If your traffic doesn't remain the same, then you're wasting money. Having a fully pimped out data center with racks on racks of redundantly load balanced servers is rather silly if you only max out some messy CPU. As such, our definition of scalability will lean towards the overall flexible nature of a scalable system, its ability to adapt to changing requirements at runtime. One term you'll frequently hear in this context, especially when talking about cloud computing, is elasticity, which perhaps more aptly describes this feature. So, whether we're vertical or horizontal means a scalable, a flexible, and elastic system is one that readily adapts to changing demand. We'll try to keep this in mind throughout the semester where we'll consider requirements that may spike hundredfold or evaporate again. For now, let's move on to security. And yes, this, by the way, is a mostly accurate depiction of what counts as security in many cases. All too frequently, the software or information technology industry treats system security as an afterthought, as something that can be added to the final product once it has met all the other functional requirements. After the user interface has been determined and after all code has been written, it is not or it is then not surprising that oftentimes people view security and usability as being directed and inversely related. This, however, suggests that the only way to reduce risk is to take away or to restrict functionality. But anytime you do that, the users will work around your restrictions or stop using your product altogether. Instead, security needs to be built into the system from the design phase on. That is, rather than starting out with a solution that provides us desired functionality and then attempting to figure out how to get it to a secure rate or secure state. We should instead begin with a secure, albeit restricted state and then slowly add functionality without compromising safety until the desired capabilities are available. That is, we need to view security as an enabling factor present at the design's conception when building our minimum viable product. In this case, we'll often discuss security failures or problems in the products or systems we encounter. And quite frequently, we will be able to point to the discrepancy in product design objectives that lead to such a problem. As such, we'll cover peripherally at least throughout almost every week, as well as in the summarizing fashion towards the end of the semester. Many aspects of security that relate directly to the computer human systems we care about. This will include the broad art of cryptography, with its ability to aid in the areas of confidentiality, integrity, and authenticity, physical security, service availability, service design, social engineering, and often generic trust. All of these should have us approach each area and topic we discuss from both a user's point of view, asking and understanding what the users actually wants when they use our systems, as well as a system or product-centric point of view. More often than not, we'll be find that these two intersect with one another more than with the adversarial perspective. Okay, now for both of these two core properties, scalability and security, we have noted that neither can be added later after the fact. To go back to our earlier example found in our data centers, you can take a mess like this and then slap on some scalability. Both scalability and security are things that you have to include in your system design right from the beginning. When that is done, the practical application of these principles yields a reduction of interfaces, endpoints, use cases, and overall variance. At this time, it's also worth noting the difference between complicated, as illustrated here on the left, and complex. A complex system may be well organized and exhibit a clear, logical structure, yet require subtle or intricate connections or components. Complicated systems, on the other hand, are irregular, unpredictable, or difficult to follow. Scalable and secure systems are less complex and much less complicated. As systems administrators will like keys. Keys is, well, remarkable not for the ridiculous outfit of their pyrotechnics or their plateau shoes. In fact, we're not talking about the band at all, but a core sysadmin principle, abbreviated as KEYS. That means keep it simple, stupid. That is, keep it simple, stupid. We are looking to reduce complexity. Complexity is the enemy. We will look to us resist the temptation to build features we do not need and instead build tools that can be combined. In that way, we will look to the Unix philosophy, which includes a critical directive to build simple tools to do thing and do it well. That is, we will create small components that like Lego blocks can be combined. Small little tools that follow the same interfaces and that fit well together. And with such simple building blocks you can build intricate, large, and yes, complex systems. The Lego Star Wars Millennium Falcon is one of their largest sets. It consists of over 7,500 pieces and to certainly is far from simple. But I think this illustrates well that we're looking for small, simple building blocks that can be combined to create complex but well-structured systems. And one part of system administration, well, and software engineering, programming, and the various other related and overlapping aspects in the discipline consists of the design and implementation of such complex systems that, because we keep simplicity in mind in the construction and use of the building blocks, will be more fault tolerant, more performant, and more flexible. And so, simplicity, the third core property of exceptional system design, is really the enabler of both scalability and security. And that's why we like keys. Now, this concept of simplicity can even be translated beyond just the design of the implementation of systems, but also to our approach of problem solving. One way to try solve complex and even complicated problems is the application of the Occam's razor. Occam's razor has been many different formulations, but the most common one is that for a given problem, the simplest explanation is usually the correct one. This is something that will be useful for you to recall when you're trying to troubleshoot complex systems, which tend to fail in complex ways, but often due to simple causes. A similar golden rule to internalize is the second law of thermodynamics, which stipulates that the entropy of an enclosed system increases with time. Applied to system administration, this tells us that things will move towards greater disorder. The more users you have, the more traffic you have, the more systems you have. All of these will contribute to more software with more bugs connecting to more other systems and so on and so on. Systems left running for a long time eventually run out of memory or disk space, as they may trigger edge conditions leading to a memory leak. Hardware will inevitably and eventually fail. Keep this in mind allows us to anticipate and prepare for the inevitable. Next up in our series of system admin laws is the Hanlon's razor. Hanlon's razor is in a way a variation of Occam's razor. Hanlon's razor states that you should never attribute to malice that which is adequately explained by stupidity. It's easy to jump to conclusions and far unfair as a nation-state actor has infiltrated your network and planted a backdoor, which changed the permissions of dev or null and which you combine upon by accident, or a user may have accidentally done so. Which explanation is simpler and thus, according to Occam's razor, more likely? Hallam's razor here deserves being called out because, especially when you focus on security, as system administrators must do as part of their job. It's easy to see malicious actors everywhere, but it's worth remembering that anytime you prevent accidental failure, you also help mitigate the risk of intentional abuse of such a failure mode. So, Hanlon's razor can help you win ground here too. Next up is the Pareto's principle. This principle states that in most cases, roughly 80% of the consequences derive from 20% of the causes and was originally applied to economics. But it turns out it applies nearly universally. I'm sure you've noticed that when you're writing a program, the general functionality, all the big parts are easy. You get about 80% done with the program fairly quickly and spend the majority of the total time on the last 20%, where you're debugging tricky issues and fine-tune the functionality. So 80% of your time is spent on 20% of the functionality and vice versa. This rule of thumb can be surprisingly useful in estimating software development time, in estimating how customers will use available disk space, what network filters will catch or prevent what traffic, and so on and so on. The 80-20 rule can be applied recursively, and you can again estimate the resources you need to spend on the vital few and what on the inevitable long tail. Then there's carp. Wait, what? That's not even a carp, that's estrogen, if you have noticed on screen. This is an ad-age named after Theodore Sturgeon, a science fiction writer who famously quipped that 90% of everything is carp. Crap. 90% of everything is crap. He said this after he had noted that 90% of science fiction literature is crude, but observing that's only because 90% of everything is crude. That is, most of everything is not outstanding. System administrators will quickly find out that this is painfully accurate as you go through software, both open source and provided by commercial vendors. It is not actually nihilistic as it sounds, but useful reminder to help you set expectations. Similarly, we are all rather familiar with Murphy's Law, right? Anything that go wrong will go wrong, or more precisely, anything that can happen will. Like Sturgeon's law, it's not quite so pessimistic, but good to keep in mind, especially when it comes to software, and in that field even more so when we're talking about software systems at internet scale. We can't excuse not preparing for something by saying, well, that are the odds of what happening. Or we would ever enter that into the field here. If it can happen, it will. Hardware drives will fail. A user will enter an invalid number into a field. A network connection will drop. And undoubtedly redundant power supplies will both fail at the same time eventually. Our job then is to prepare for these eventualities, to anticipate the possibilities and build robust systems to function under those circumstances. Finally, as we are talking about the possible things happen and then logically of impossible things not happening, we end up with the realm of philosophy to help us troubleshoot our system's causality or causality. For every effect, there must be a cause. Things don't just happen. Systems don't just break. There's a reason for why your software exploded, for why the load balancer shifted traffic away from a healthy origin VIP, for why your database is currently locked, and for why your outbound traffic filter didn't kick in. Sometimes, the causes for these effects are hard to find, but they're there. The various rules and loops just mentioned will hopefully help you cut out the less likely explanations and guide you in finding the true cause. All it takes is perseverance and dedication to finding the cause of the problem. Okay, so these were just some of the every systems admin's favorite laws. You'll find that we'll reference them throughout the semester, and I bet you will years from now in your jobs run into situations where you will remember them. Of course, there are many more similar laws and observations, and we will, without a doubt, sprinkle some of them in each week. But for today, I think we'd have enough. Okay, thank you very much.